Hi everybody, I hope this video finds you well. Today we're going to be discussing some additional sort of notes and comments about using the LSR to make predictions, and then we'll be working through an example, seeing sort of how these different comments about predictions actually work out in a sort of real-life example. So you'll remember from the last video, we sort of introduced the idea that if we can establish that there is a correlation or a relationship between two variables, the next natural step is to try to model that relationship. And the model that we're using in our class is a linear model, namely the LSR. And we saw that once you actually get that linear model, what you can use that linear model for is to make predictions about your data set. So we want to give a couple extra comments about predictions. The first of these is we'd like to introduce the idea of the residual. And the residual is basically a way of measuring the error that occurs when we make these predictions. So we're going to give a definition here. The residual, and that's the important idea here, of a data point is, well, the way you calculate a residual is you take the actual response minus the predicted response. And if you prefer a notation, that's taking the actual y value minus the predicted y value. So that's how we calculate a residual. We take the y minus the predicted value of y. A couple things about the sort of residuals here. We're going to do a lot with residuals in our sort of next video, but a couple comments that you should keep in mind here. If the residual is positive, what this means, right, is if the residual comes out as a positive number, that means the actual is larger than the predicted. So what that means is that the sort of model underestimated. And if the residual is negative, well, if the residual is negative, then that actual there must have been smaller than the predicted, which means that the model overestimated. Okay, so whenever you hear this sort of term residual thrown around, all that basically is doing is measuring how different what actually happened is versus what was predicted. Now, because this is a subtraction, do keep in mind that the order here is very important. We always start with the actual and then subtract the predicted. All right, let's talk about our second idea here, extrapolation. Extrapolation is something that we're actually trying to avoid when making predictions. So, extrapolation is when we use the LSR far away from the observed explanatory range. We do not trust predictions that come from explanatory values far from our data set. What this sort of comment here means, this idea of extrapolation, is that when we sort of build a linear model, we're building it based off of a data set that we observed and that we used to convince ourselves that there was a relationship between the two variables. Now, that data set is going to have some range of explanatory values, right? There's going to be sort of a lowest explanatory value and a highest explanatory value. What we're sort of saying in this is that we trust our model in that range, right? We trust our model sort of where we observe the data, but we do not trust that model far away from that data set. You can sort of imagine like examples of where that would be the case. Suppose we were, sort of studying like how people do on an exam based on how long they study. So maybe we observe some people who study like 2 or 3 hours for an exam, some people who study like 5 or 6 hours, and some people who study like 8 or 9 hours. And we could build a model that sort of tells us how we expect those people to perform on an exam based on the amount of studying. Now, we wouldn't want to use that model to predict how somebody would do if they studied for like 40 hours for the exam. Why? Because nobody in that data set studied anywhere near 40 hours, right? Some of them, we said, studied maybe 1 or 2, some studied 5 or 6, some studied 8 or 9, but no one was anywhere near 40 hours. So how do we know what's going to happen for somebody that is going to study 40 hours? There was nobody similar to them in our data set, so we shouldn't try to make predictions. That's exactly what extrapolation is all about. All right, the last thing we're going to mention is the coefficient of determination. So we're going to give a definition here. The coefficient of determination is a measure of predictive power. So in other words, the coefficient of determination tells us how good our predictions are. We never like predictions that are outside our data range. That's what extrapolation is saying. But when we're inside our explanatory range, we still need to measure how good those predictions are going to be. And the coefficient of determination does that. The coefficient of determination is R squared. So the way you get the coefficient of determination is you literally square the correlation coefficient. Remember, squaring something just means multiplying it with itself. Now, if you're typing data into your calculator and you're using that L1 and L2 and the ln reg ax plus b, R squared will be calculated for you, right? When we've done our ln reg ax plus b, we've seen that we can get the a and b values, right? The slope and the intercept. We've used that we can get the correlation coefficient R, but R squared is also given to us. If for some reason you're not typing data in to your ln reg ax plus b and you just know the R value, well, you can calculate R squared by literally squaring the R value. So just be aware that the coefficient of determination is directly related to the correlation coefficient. So what does the coefficient of determination tell us? Well, R squared tells us the percentage of variation in the response variable that is explained by changes in the explanatory variable. So what we're saying there is that the higher the R squared value is, the more of the variation, the more of the sort of spread that we're seeing in our data is actually explained by our explanatory variable. So in other words, the better the explanatory variable is at explaining what's going on. If we get an R squared that is like 0.9, which would mean that it's 90%, we're basically saying that 90% of the fluctuation in the response is explained by having different values of the explanatory. That means that 10% of the fluctuation must be explained by other variables or other factors. If we get an R squared that's only, say, 0.25, that means only 25% of the variation is explained by the explanatory variable. The other 75% is all other things that we're not studying. So you can imagine that the higher the R squared value is, the more sort of powerful our LSR is at making predictions. So we really want nice high R squared values to make sure that we're comfortable making predictions with our LSR. All right, so these are three things just to sort of keep in the back of your head when we're talking about predictions. You should be comfortable sort of measuring the error through a residual. You always want to avoid extrapolation. And sometimes, we'll be asked to talk about the coefficient of determination. Now, I will say that in real life, coefficient of determination is very, very important. It is a sort of complex idea, though. So for our class, you really want to just sort of focus on this interpretation here and specifically realize that it's sort of written in a form that you can fill in. If you need to discuss the R squared, you just need to know that sort of percentage. You need to know what the response variable is, and you need to know what the explanatory variable is. If you know those three things, then you can just literally interpret it by using this format here. All right, let's go ahead and take a look at an example, getting us sort of some more practice with some of the things we introduced in previous videos, as well as discussing these sort of three new ideas. All right, so let's go ahead and take a look at this example here. So we've got a researcher who's studying the relationship between the length in inches and weight in pounds for brown bears. So what they do to study this is that they study 20 brown bears and they build this model here. So they build this model that says that the predicted y is equal to 13.8x minus 397. And they've calculated that the r value is 0.76. Now you'll notice that this is very different in terms of just like the information we're being given here. We're not being given the raw data of the 20 bears. Instead, we're being given sort of the summary statistics of the LSR here and the correlation coefficient here. And then we're reminded that the variable x is the length in inches. So that's telling you that the length is the explanatory. And the variable y is actually the weight in pounds. So that's going to be the response. Then they also tell us this note that the sample ranged from 65 inches to 95 inches. And what this would be is that this is the explanatory range. In other words, this is sort of telling us that the bears that we looked at were anywhere from 65 inches up to 95 inches. And that's where we'd sort of want to make our predictions. All right, so we've got a bunch of different things that we're going to do with this. We're going to talk about whether or not there's enough evidence for a correlation. We're going to interpret the slope. These two things here are going to be reviewed. We've done those in some of the previous videos. And then the sort of C through F here are all going to be these sort of newer things. So we're going to talk about the coefficient of determination. We're going to make some predictions. And then in part F, you can see that we're going to be calculating a residual as well. So this will give us a chance to sort of practice all the things we've introduced in this video. Now, before we get into just computing everything, I do want to make a mention of that this example here also is for you guys to sort of see why people bother building sort of linear models in real life. If you imagine, right, this is a sort of a situation that maybe, a wildlife researcher, or zoologist, something like that, would want to study. And if you think about this, measuring the sort of length, right, that explanatory variable, that's not particularly hard to do. Even if the bear is not in like captivity or something, you can figure out how long the bear is by, taking a photograph and then sort of knowing how far you were away and using a scale and that sort of stuff. But knowing the weight of a bear, that's very challenging, right? Unless you can actually get the bear onto some sort of scale, you're not going to know how much it actually weighs overall. So the idea here is that statistics provides us a way to model something that's hard to measure, the weight, based on something that's easy to measure, the length. And if we can build a good model for that, then we're comfortable understanding a variable that's hard to measure by using one that's easy to measure. So you should sort of keep that in the back of your head because that's the big idea in this sort of modeling section of correlation and regression. All right, enough about that sort of stuff. Let's go ahead and actually just try some of these pieces here. We'll do that on the next page, so we'll have a little bit more space, but of course the problem will sort of still be there. And again, I would strongly recommend that, as we do this, you follow along and try these pieces as well, because this is definitely sort of in the vein of what you guys would expect to be able to do with this sort of information. So let's go ahead and take a look with this. All right, so there's our problem there. We're just going to sort of go through piece by piece here, right? The first thing that we wanted to do was talk about whether or not there was enough evidence. So we know how to do that. We know that that basically means we need to look at this correlation coefficient and decide if it's strong enough. Well, the way we do that is we go on to table E. To use table E, we need to know how many were in this sort of sample. They notice that they mentioned that there were 20 brown bears, so we know that our N here is 20. Let's go ahead and take a look at table E and find that critical value. So there's table E. N here is 20. We're always using that 0.025. Intersecting those together, looks like we should get 0.4438. So we'll go back and record that critical value. The critical value here is 0.4438. Okay, now we compare. We take our absolute value of our correlation coefficient. Again, absolute value just makes everything positive. It's not necessary here because our R value is already positive, but it's just a good habit to be in. We compare this R value against the critical value, and of course we can see that the R value is greater than the critical value. So that means there is enough evidence for a positive correlation. So in other words, we are convinced that the length of a bear in inches really does explain or help predict the weight in pounds for those bears. Okay. Might not be the only factor, might not even be a causal factor, but we definitely know that we have enough evidence for a positive association, a positive correlation. All right, the next thing we want to do is we want to talk about the slope. Well, determining the value of the slope is nice and easy. It's this guy right here, right? Normally we would look it up on our calculator from using that ln reg ax plus b, but the model's already given to us, so we can just record that value. It's 13.8. Now, what does that 13.8 mean? Well, we know that algebraically, that means that when we go up 1 in x, remember, the slope is always about going up 1 in x, so that part will never change. The slope here is what happens to y. So that since it's positive, that means we go up 13.8 y. Okay, now let's break down what x and y actually is. Well, x we know is the length. So when we go up 1 in length, how do we know that x is length? Well, they remind us that x is the length. And that means we go up 13.8 in the weight. Now, 1 length and 13.8 weight doesn't quite make a lot of sense because we didn't put any units there. So we can look back and see that the length is being measured in inches and the weight is being measured in pounds. So when we go to write our sentence, we can use those units. So we're saying our model predicts that for each additional inch, I should say inch in length, a bear weighs an extra 13.8 pounds. So what we're saying is that according to our model, right? According to our model, for every additional inch that the bear is sort of in length, that means that they're going to weigh about an extra 13.8 pounds. So basically that's sort of telling us the relationship, the sort of size of the relationship. Each inch doesn't contribute an additional pound. It doesn't contribute 100 pounds. It contributes about 13.8 pounds. All right, in the previous sort of example, we also took the time to go ahead and interpret the intercept, right? The intercept would be this value here. But you'll notice that in the original statement of this problem, we sort of didn't ask to go over the intercept. And that's because if you think about it here, the intercept doesn't really make any sense. Because the intercept is when x is 0. And if you think about what x being 0 in this case would mean, x being 0 in this case would mean that the length is 0. So that means that there's some bear out there that's 0 inches long. That doesn't make any sense in real life, so we don't even bother talking about the intercept in this case. All right, let's go ahead and move on into some of the newer things. For C, we want to get that coefficient of determination. So what that means is we need to get that R squared. Now, this time we're going to have to calculate the R squared sort of manually because all that we don't have access to the raw data, but we do know the R value right there. So let's go ahead and get that. R squared is going to be 0.76 because that's the R value, and then we're going to have to square that. If we do that on our calculator, so we just type in 0.76 squared, you have a square key on your calculator, or you can just do 0.76 times 0.76. And you evaluate that, and you should get 0.5776. So that is the value of the coefficient of determination. Now we need to interpret it. So what does this mean? Well, we always just go ahead and write this as a percentage. So we'd say 57.76% of variation in, well, what is the response variable? It's the weight here. So 57.76% of variation in the weight of brown bears is explained by changes in their, well, whatever the explanatory is, in this case, length. So what we're saying is that changing the length of these bears, having them be sort of, some of them are longer, some of them are shorter, etc., right? That explains about 57 or almost 58% of the variation in their weight. Now, the other percentage out there, the other like about 42%, that must be explained by other factors, not their length. But that tells us that close to about 60% of the variation we're seeing can be explained just by understanding that they have different lengths. So that tells us that our model is a pretty good predictor because it's accounting for a sizable chunk of the variation. All right, let's go ahead then and make some predictions. So we wanted to do the weight of a 75-inch bear. Well, whenever you want to do a prediction, that just means you're going to be plugging in to your model here. So let's do that, right? So we would get our y hat, 13.8, plug in that 75 minus that 397, and we can just use our calculator to do that. 13.8 times 75 minus 397, we should get 638. So we would say that the 75-inch bear should weigh approximately 638 pounds. Now, the question also asked us, would we trust this? Well, how do we determine if we would trust it? Well, we ask ourselves, did we see bears that were sort of similar in length to this? Well, if we look back, we know that the bears sort of were from 65 to 95 inches long, and 75 inches is right in there. So we would say, since 75 inches is in the explanatory range, which was 65 to 95, we do trust the prediction. So we're comfortable making that prediction because there were bears in our sample similar to the one that we're trying to make this prediction about. All right, let's try another prediction. We want to do the weight of an 120-inch bear, so a much larger one. We do the same kind of computation, right? We need to make a prediction, so we plug into our model. So there we go. 13.8 times 120 minus 397. So 13.8 times 120 minus 397, and you should get 1259. So on an 120-inch bear should weigh approximately 1,259 pounds. Okay, now how do we feel about that prediction? Well, since 120 inches is far outside the explanatory range, right? Remember, we only saw bears up to 95 inches. We do not trust. So, while there was nothing mathematically wrong about plugging into our model, we don't really trust that prediction because we didn't see any bears that were similar to the one that we're trying to make this prediction about, right? The largest bear, according to our information that we studied, was one that was 95 inches. This one that's 120 inches is far beyond that, so there's no reason to believe that our model will apply to it. All right, the last thing we want to try to do here is we want to try to go ahead and calculate a residual. So we had a bear that was 72 inches and 550 pounds, and we want to get its residual. Okay, so to get its residual, right, remember that the residual is the y minus the predicted y. Now, we know the actual y value, right? We know that its actual weight was 550, right? So we know y is 550. So what we need to know is its predicted weight. Well, how do we find a prediction? Well, we always go ahead and use our model. So let's go ahead and do that, right? We get our predicted by doing 13.8 times x. So what is our x value here? Well, it's going to be the explanatory, so 72. So we'll pop in our 72 there, minus 397. Let's go ahead and calculate that. 13.8 times 72 minus that 397. And we should get that that's 596.6. So that's our predicted. So what is the residual then? Well, the residual would be the actual 550 minus the predicted, which would be 596.6. And if we do that, 550 minus 596.6, this would be negative 46.6 pounds. So the sort of residual or the error for this bear would be negative 46.6 pounds, right? That's because they actually weighed 550 pounds, but we predicted it should have been 596.6. According to our model, is the bear under or overweight? Well, that's pretty simple, right? According to the model, it should have weighed close to 600 pounds. It's only 550. So the bear is underweight according to the model. And there we go. That's just working through and using the sort of LSR to make predictions. The couple main things from a computational standpoint you guys should be aware of is that anytime you want to make a prediction, that just means plugging in the explanatory into the model, right? That's what we were doing in all these examples. Then, in terms of trusting a prediction, it all boils down to understanding if you're inside that explanatory range. In our next video, we'll talk more about using the residuals to understand whether or not our choice of model is the right choice of model, and we'll do some more computational practice calculating those residuals.